Every modern application depends on a promise most people never think about. You update a database and you trust the update either fully happens or doesn't happen at all, never something stuck halfway. That promise has a name and it's the first letter of ACID, atomicity. The next several minutes, we're breaking down exactly what that word means, why database is treated as completely non-negotiable, and what's actually happening under the hood to make that all-or-nothing guarantee real, even when the power cuts out mid-write. By the end, you'll understand not just the definition, but the actual mechanism, the write-ahead log that makes it possible, and exactly how atomicity fits alongside the other three ACID properties without being confused for any of them. Let's start with the failure case atomicity exists to prevent. Imagine transferring money between two bank accounts. Your account gets debited, the other account gets credited, two separate writes, two separate operations. But what happens if the system crashes after the debit succeeds but before the credit happens, money vanishes, it left one account and never arrived in the other? This is exactly the kind of failure that databases are built to prevent, and the property responsible for preventing it is atomicity. It makes a simple but powerful promise. A transaction either completes entirely or it doesn't happen at all. There is no partial state, no in-between, no half-finished operation left behind for someone else to discover. Every relational database you've ever used, Postgres, MySQL, SQLite, all of them builds this guarantee in as a foundational feature, not an optional extra you opt into when convenient. Let's make this precise. A transaction is a group of one or more operations that the database treats as a single, indivisible unit. Indivisible is the key word. It's literally where the name atomicity comes from, borrowed from the Greek word for uncuttable. From the outside, observers never see a transaction half done. They see it as one atomic action. Picture our bank transfer as a single unit. Debit account A, credit account B. Atomicity doesn't care that there are two separate writes happening internally. It guarantees both writes are bundled together as one logical operation. Either both writes land permanently or neither one does. The database will never apply only the debit and skip the credit. This indivisibility is what lets every other part of the system reason about data simply. Application code, other transactions, other users, they all see a database that only ever moves between complete, consistent states, never corrupted in between. So what actually happens without atomicity? Picture the same transfer, but the system has no atomicity guarantee at all. The debit operation writes successfully to disk. Then right before the credit operation runs, the server loses power. When it restarts, the debit is sitting there permanently applied. The credit never happened. The money is simply gone, not in account A, not in account B. Multiply this across thousands of transactions per second, and a database without atomicity becomes a system that slowly bleeds out trust. Partial writes pile up. Some rows reflect operations that should have been bundled with other rows that never made it. There's no way to tell just by looking at the data whether a multi-step operation finished or failed halfway. This is the exact failure mode atomicity exists to eliminate, and it's why every serious relational database treats it as non-negotiable, not an optional feature you can turn off. Atomicity guarantees exactly two possible outcomes for any transaction and nothing in between. The first outcome is commit. Every operation in the transaction succeeded and all of its changes become permanent. The second outcome is abort, sometimes called a rollback. Something failed partway through and the database undoes every change the transaction had started to make, returning the data to exactly the state it was in before the transaction began. There is no third outcome. A transaction cannot be mostly committed. It cannot leave 3 out of 4 operations in place and discard the fourth. From the database's perspective, partial success simply isn't a valid state. The only valid end states are fully applied or fully erased. This binary outcome is what application developers actually rely on. Wrap your operations in a transaction and you only ever need to handle 2 cases, not an explosion of partial failure scenarios. Here's the part most people never see. How does a database actually deliver on this promise when a crash can happen at any instant mid-write? The answer is a mechanism called the write-ahead log or WAL. Before the database modifies the actual data files, it first writes a record of the intended change to a separate, penned-only log file. Only after that log record is safely flushed to disk does the database go and modify the real data. This ordering is the entire trick. If a crash happens before the log entry is written, nothing happened yet, the original data is untouched. If a crash happens after the log entry is written but before the data file update completes, the database has a durable record on disk of exactly what it was trying to do. On restart, it can read that log and finish the job correctly, rather than leaving things half-changed. That write-ahead log is also exactly what makes rollback possible. When a transaction aborts or when the database restarts after a crash, it replays the log from the last consistent checkpoint. For every transaction that fully completed before the crash, the log lets the database redo those changes, guaranteeing they aren't lost. For every transaction that was still in progress when the crash happened, the log lets the database undo any partial changes, erasing them as if they'd never been attempted. This recovery process runs automatically every time the database starts up after an unclean shutdown. You never have to manually inspect which rows are trustworthy. The WAL replay mechanism does that reconciliation for you deterministically, using nothing but the log records that were durably written to disk before the crash occurred. It's worth being precise about where atomicity ends and the other ACID properties begin, because they get conflated constantly. Atomicity is only about the all-or-nothing guarantee for a single transaction set of operations. Consistency is about the database never violating its own defined rules and constraints. Isolation is about how concurrent transactions are kept from interfering with each other while they're running. Durability is about committed changes, surviving a crash once they're confirmed. Atomicity and durability work especially closely together. The write-ahead log we just covered is actually the shared mechanism underneath both of them. But they answer different questions. Atomicity asks, did this transaction happen completely or not at all? Durability asks, once it happened, will it survive a power failure? Keeping these four properties distinct in your head is what makes ACID actually useful as a mental model, instead of a blurry acronym. Let's bring it all together with one real transaction. Picture this exact sequence. Begin, then update account set balance equals balance minus 100 where id equals 1, then update account set balance equals balance plus 100 where id equals 2, then commit. The moment begin executes, the database opens a transaction boundary. Both update statements execute, but their effects are not yet permanent, they're staged. Every byte of this is first recorded in the write-ahead log. Only when commit executes does the database mark this transaction as durably finished, and both balance changes become permanently visible together. If anything fails between begin and commit, a constraint violation, a crash, a dropped connection, the database rolls every change back, and it's as if neither update ever ran. That's atomicity in one sequence of statements, a multi-step operation collapsed into a single all-or-nothing unit of work. Thanks for watching.